Welcome to an intro to instantaneous rates of change. So the idea here is we're looking at rates of change. We're looking at rates of change. So for example, we could be talking about miles per hour. We could be looking at dollars earned per day. We could be looking at something like feet per second. Right? Rates of change, we're just looking at how one unit changes as another one changes, how one measurement changes as something else changes, right? If we think about, say, miles per hour, when you're driving in a car, the speedometer tells you precisely how fast you're moving at that moment, right? So when driving in a car, the speedometer tells us precisely, well, to the nearest mile per hour, precisely how fast you are moving at any point in time. And this, sorry, that should be how fast, not as fast. How fast. This how fast you are moving at any point in time, that is what we refer to as the instantaneous rate of change. It's the speed at that moment. So this is considered to be the instantaneous rate of change. But if we don't have a speedometer, we don't really have a way of measuring how fast we're going at a particular moment. Usually all we can find would be the average rate of change, the average speed. So without a speedometer, we only know average speed. So we are wanting the instantaneous rate of change. And the question is, how on earth can we find that if we don't have a speedometer to do the measuring for us? So let's go ahead and take an example. For this example, suppose a ball is dropped from the top of a 100-foot building. Then its height above ground in feet at t seconds after release is given by the function f of t is equal to negative 16 t squared plus 100. Those of you who have taken some physics have likely seen this sort of formula before. If you have not, don't worry about it. I'm giving you the formula. And our goal now is going to be to figure out how fast is the ball falling at 1 second after release. So our thought process here we don't have a speedometer, right? We only know location and time. So we don't have a speedometer. Which means at this point, we only know height and time. So at any given time after release, we can figure out the height of the ball. And so that means that we could find average speed. So we can calculate average speed. And we can try to use the average speeds then to approximate the actual speed. So we can use average speed to try to predict the speed at one point in time. So the first thing we're going to do here is go ahead and just find the average speed between 1 and 2 seconds. So we want the speed at 1 second. Let's do average speed from 1 to 2 seconds. So to find the average speed, we need to know the distance traveled and then we'll divide that by the time it took to travel that distance. So in this case, we're going from 1 to 2 seconds. Right? So to find the distance traveled, we just can do the distance at or the height at 2 seconds minus the height at 1 second. So we'll do the height at 2 seconds minus the height at 1 second. And then for time elapsed, we just have 2 seconds minus 1 second to figure out how much time has passed. So from here, the height at 2 seconds was just f of 2. And the height at 1 second is just f of 1, right? The function f told us our height. And then 2 seconds minus 1 second, we have 1 second has passed. So our function, just a reminder, since it's out of the window, we had that f of t was equal to negative 16 t squared plus 100. So f of 2, we are looking at negative 16 times 2 squared plus 100. And then from that, we are subtracting f of 1. We have negative 16 times 1 squared plus 100. All over 1. Again, up top, we're talking about feet. Down below, we're talking about seconds. Then negative 16 times 2 squared is negative 64 plus 100 would be 36. And we are subtracting off negative 16 plus 100. We are going to subtract off 84. And this becomes negative 48 feet per second. Now speed technically is positive. So technically for average speed, we should do the absolute value of the height at 2 minus the height at 1. The absolute value, the absolute value. So the speed we would have 48 feet per second as the speed it's falling. The velocity comes with direction. We would leave that sign. So the velocity we would say was negative 48 feet per second. The negative indicating that the ball is falling downward. Right, so we just found that between 1 and 2 seconds, the ball was falling at an average speed of 48 feet per second. But now we're going to go narrower because we want precisely at 1 second. So instead of from 1 to 2 seconds, let's go ahead and find the average speed between 1 and 1.1 second. So again, we have that the average speed would be equal to the distance traveled divided by the time elapsed. So we would be looking at the height at 1.1 seconds minus the height at 1 second. And then time elapsed, we're just looking for the difference, 1.1 seconds minus 1 second. So the height at 1.1 seconds was given by f of 1.1. And we are subtracting off f of 1. We have 1.1 minus 1, or 0.1. And then just as a reminder, again, f of t was equal to negative 16t squared plus 100. So as we go to plug in, that first f of 1.1, we have negative 16 times 1.1 squared plus 100. And then we are subtracting off f of 1. So we have negative 16 times 1 squared plus 100. All divided by 0.1. And then if we go ahead and plug those into a calculator, we wind up getting, we have 80.64 minus 84 all over 0.1, or 3.36 divided by 0.1. And that is 33.6 feet per second. So again, sorry, negative 33. It should be negative 3.36 and negative 33.6 feet per second. Again, technically, average speed is positive, so we would have absolute value around the height to guarantee we get positive. And so we wind up getting this average speed would be 33.6 feet per second versus the average velocity would have that negative since it's falling down. So negative 33.6 feet per second. So we went from average between 1 and 2 seconds was 48 feet per second. Now we've dropped down to 33.6 feet per second. The question then becomes, what is the instantaneous speed at precisely 1 second, or what is the velocity at precisely 1 second after the ball was released? So we want to know essentially what would happen if we picked times closer and closer to 1 second. Okay. So what if we picked, instead of going, so we've done from 1 to 2 seconds. And then we've done from 1 to 1.1 second. But what if now instead we look at one to 1 plus h seconds, and then let h get small. So, and let h go to 0. So once again, we would have our average speed. Let's just do average velocity this time around. For our average velocity, we're going to do the distance traveled divided by the time elapsed. So we're going to have the height at 1 plus h seconds, and then subtract off the height at 1 second. And then divide by, we have 1 plus h seconds minus 1 second. So we have f of 1 plus h. We subtract off f of 1. And we divide by h. Now, does this look familiar? Well, this is the difference quotient at x equals 1. So this is the difference quotient at x equals 1. So if we simplify this, let's do a little color coding. Oops, sorry about that. So let's find f of 1 plus h. So f of 1 plus h, we are looking at negative 16 times 1 plus h, the whole thing squared, plus 100. And then f of 1, we've already figured out, but we can do one more time. So f of 1, we have negative 16 times 1 squared plus 100. And then we are subtracting these and dividing. Oh, sorry. Yeah, we can do this. And dividing by h. I did this all in one go. So the purple is our f of 1 plus h. The blue is our f of 1. So f of 1 plus h squared, or sorry, 1 plus h squared. We have our negative 16 out front. 1 plus h squared, we are doing 1 plus h times 1 plus h. 1 plus h times 1 plus h becomes 1 plus 2h plus h squared. Then we have our plus 100. On the right, we are subtracting off 84. And dividing by h. So our f of 1 plus h, now we will simplify some more. We will have a negative 16 minus 32h minus 16h squared plus 100. And we are subtracting off 84 and dividing by h. Now, if we do negative 16 plus 100 minus 84, like terms, everything I have highlighted in, or underlined in green, if we combine those, that just goes to 0. And so this then winds up simplifying to negative 32h minus 16h squared divided by h. So again, this right now is our average velocity. And we could simplify this if we wanted. We'll go ahead and take the limit at this point. So we were interested in what happens as h goes to 0. So now we're going to let h head to 0. So we are essentially wanting to take the limit as h goes to 0 of negative 32h minus 16h squared all over h. So this is going to be a scenario where both the top and the bottom are going to 0 over 0. So we need to simplify. Our numerator, we can factor out a negative 16h, and we are left with 2 plus h. And then on the bottom, we have h. We can go ahead and cancel out, or cancel the h that was factored out with the h in the denominator. And at this point, we can go ahead and just plug in our 0 for h. And we wind up getting negative 32. So this, what we've been doing off the side, is our instantaneous velocity. If we took 2 times closer and closer and closer to just being precisely at 1 second, ultimately that average speed goes to negative 32 feet per second. So the ball is falling at 32 feet per second, 1 second after release. All right, so that's sort of one specific contextual or context where we can find the instantaneous rate of change. And we did that by looking at a bunch of average speeds and then letting the two endpoints get closer and closer together.